All right, we're going to finish up 4.1 Part A with our last example. So in the last video, we left off, whoops, too far. We left off after talking about a nautical mile, and knots, right, is 1 nautical mile per hour. So how do we convert from knots to miles per hour speed? We use this equivalence, right? 1 nautical mile is 1.15 normal miles or statute miles. So looking at number 9, right, we had just talked about longitude and latitude and what those mean. So Los Angeles and San Francisco have almost the same longitude, right? Not exactly, they're not directly on top of each other, north on top of each other, but they're close enough for this example. Their latitudes, however, north to south, right, the horizontal lines across the globe, are very different. One is 34 degrees and 3 minutes, and one is 37 degrees and 47 minutes. So San Francisco is 37 degrees latitude, whereas Los Angeles is only 34 degrees latitude, respectively. So determine their distance, right? So assuming that their longitude are close enough that we can just ignore it, what's the distance in terms of their latitudes? Well, if we subtract them, they are 3 degrees and 44 minutes apart in longitude. So if I convert this degrees, 30 degrees times 60 degrees per minute, into minutes, they're 224 minutes apart in longitude. But again, remember, 1 minute measured from the center of the Earth traces out an arc length of 1 nautical mile on our Earth. So 224 minutes apart in longitude is the same thing as saying, well, they're 224 nautical miles apart. Or now convert, right, 224 nautical miles times 1.15 miles over 1 nautical mile, right? Just multiply. They're about 258 miles apart using what we've learned. Now, realistically, if you wanted to know how far apart Los Angeles and San Francisco are, you'd probably use Google Maps. But then again, that wouldn't give you the distance as a straight, like how the bird flies per se. It would give it to you in terms of, roads and driving directions. All right, so that's technically the end of A. Part B begins here. So we're going to look at areas and perimeters of sectors specifically. So example 10, a 30-degree sector is cut from a circular disc with a radius of 12 centimeters. Determine the area and the perimeter of this sector. So remember, S here is indicating arc length, so the distance from this point to this point. So again, the area of a sector is a fraction of the area of a circle. So what fraction of my circle is cut out here? Well, how many degrees are in an entire circle? 360 degrees. So my area is going to be just my central angle divided by 360, because then the degrees cancel out, and that is the fraction of my circle, times the area of a circle, which is pi r squared. So 30 over 360, pi times 12 squared, multiply, simplify, it's 37.7 degrees, 37.7 centimeters squared, or square centimeters would be the area. Now the perimeter, again, perimeter is the total distance around. So if you were going to take a walk and walk around this sector, you'd walk 12, S, and then 12. So you'd walk the arc length plus 2 radii. So S plus 2R. So again, what was S? Well, again, S is a fraction of the circumference. And what's my fraction? It's 30 out of 360 degrees. Out of what's the circumference? That's 2 pi r. My r is 12. So again, I'm going to have, that's my arc length plus 2 radii. Combine like terms, simplify, you're going to have 2 pi plus 24. Because again, this is all going to simplify out nicely. 30 times 12 is just 360. So 2 pi plus 24 is roughly 30.3 centimeters. All right, example 11. Calculate the area of a sector whose central angle is given to you in radians then, not in degrees. So if it's theta radians. Okay, so again, central angle in radians divided by, well, how many radians are there? How many radians are there in there's an extra R there that does not belong there. Yikes. error, typo, please scribble that out, right? Central angle in radians divided by how many radians are in a full circle. There are 2 pi radians in a full circle. So this extra r here does not belong, right? So maybe I was going for rad for radians, right? So there's 2 pi radians in a full circle. So that's just theta over 2 pi times the area of my circle, pi r squared. So if I write this over here, so that's theta over 2 pi times pi r squared. My pi's are going to divide out. And what I have is essentially 1/2 theta r squared, or 1/2 times theta r times r. Now again, if you remember theta r, that's just our arc length s. So if you think about this arc, it's very similar to the area of a triangle, which was 1/2 base times height, right? So if I angle it this way, like s is kind of like my base. My height is r, right? So that's another way, if you're given your angle in radians, to remember if you're trying to memorize the formula. Again, to me, memorizing it is not worth it. I would rather just remember the area of any sector is fraction of the circle times area of the circle, right? And how do you get the fraction? You take the degrees out of 360, or you take the radians out of 2 pi. All right? So, typo, fix. Shouldn't be an extra r. I'll go back and I'll fix that later. All right, so example 12 now. Let's talk through this one. So Austin and Jack leave Charleston Harbor on different cruise ships. One ship travels at a bearing of 39 degrees, 42 minutes. So again, from true north, one ship's going to go this way, 39 degrees, 42 minutes. And the other ship at 117 degrees, 26 minutes. So again, 180 would be directly south, 90 would be directly east. So 117 is going to be somewhere this way. So after both boats have traveled 120 miles, so 120 miles there, 120 miles there, how far are Austin and Jack apart? So the distance. All right, so in keeping with the theme of this section, right, technically could I draw a very straight line and use some of our trig properties that we haven't gone over yet in this class? The law of sines is what I would use and what we will use later on. But for now, right, this angle here, call that theta, right, 120, 120, that's not 90 degrees, even though it looks like it, right? If I do 117 degrees and 26 minutes minus 39 degrees, 42 minutes, I'm going to get 77 degrees, 44 minutes. How? Again, here I've got it stacked. What's 26 minutes minus 42 minutes? You can't do that. So you have to borrow a degree. Again, what is a degree? It's 60 minutes. So really this becomes 86 minutes. 86 minutes minus 42 is going to be 44 minutes. And that's how I'm getting 44. 6 minus 9, again, I'm going to think of that as 16. 16 minus 9 is 7. And then I'm going to have 10 minus 3 is 7. So 77 degrees, 44 minutes. So that's my angle theta. Now the distance apart is going to be pretty close, not exactly, but approximately that arc length traced out by theta. So what is that distance s, the arc length? Again, it is the fraction of my circle times the circumference. Here's my circumference, 2 pi r. So what's the fraction of my circle? Well, okay, so it's out of 360 degrees. So this is 77 degrees plus, again, 44 minutes. If I want to convert it to degrees, there's 60 minutes in 1 degree. So 44 over 60 degrees, add that together, then divide by 360, then multiply by this, right? You're going to be about, not exactly, 162.8 miles. Again, later on when we learn about the law of sines, we'll be able to find this more accurately, more precisely. Okay. Number 13, Thomas and Cole have a bike race. Thomas's bike has 26-inch diameter wheels, and he can pedal them 300 revolutions per minute. So again, RPM is revolutions per minute. Cole's bike has 30-inch diameter wheels, and he can pedal them 270 revolutions per minute. Convert each speed to miles per hour. So again, if his bike has a 26-inch diameter, that means the radius of his wheels are 13 inches. So looking at Thomas first, 300 revolutions per minute. Again, I want to go to miles per hour. So I want this minutes to be converted into hours. So 60 minutes are in an hour. So I'm done with the denominator. Now I need to convert revolutions to miles. So first, revolutions to a single distance, right? We did this already in the last video, right? To go from here all the way around, that's my circumference, which is 2 pi r. So 1 rev is 2 pi r. So 1 revolution is 2 pi r, 13 inches, right? So 1 revolution would be this. And so converting from inches to feet and feet to miles, multiply it all out in your calculator, you're going to get about 23.2 miles per hour. Likewise, for coal, 30-inch diameter means R is going to be 15, so it's the exact same setup. What's the only difference? My radius is 15 here, and I am 270 revolutions per minute. So he is going 24.1 miles per hour. Now he's going faster, even though his revolutions per minute is less. How does that make sense? Again, he's on a bike with larger wheels, so it's going to naturally take a little longer for that larger wheel to go all the way around. Right? So again, this is also how you can compare revolutions per minute. You can't just compare those two speeds and say, oh, who's faster? You have to look at how big the wheels are, and so converting this way. All right, last example before I release you to work on some practice problems on your own. So 2 airport control towers are 600 miles apart. So here's control tower 1, here's control tower 2. They are 600 miles apart. Audit is flying a plane between the towers on a bearing of 330 degrees from the first. Okay, so stop. So here is north. So 330 degrees from north would put me here. So he's flying, and his plane is currently, let me see if I can draw an airplane. Here, that kind of looks like a bird. I have no idea. Anyway, he's flying his airplane, and currently, he's probably headed more toward this way. And he's currently 330 degrees from this guy. That's what his bearing is. Which means 330 plus 30 more is 360. So what's the angle from this horizontal line here? That's 60 degrees. And he is 60 degrees from the second. So again, here's north. From the second, that's 60 degrees, which means this angle here is 30 degrees. And I've got a nice 30, 60, 90 triangle right there. So the angle here is going to have to be 90 degrees, right? How far is he from each tower? So distance x and distance y. That's what I'm looking for. So from the diagram, as long as you can draw your picture well, and from the relationship of a 30, 60, 90 triangle, which, do we remember that relationship? If I draw myself a 30, 60, 90 triangle here, right? This guy's 30 degrees, this guy's 60 degrees, 90 degrees. The short side is half the distance of my hypotenuse, right? So depending on how you learned this in trig, you might have learned this as A times rad 3 and 2a. And again, the proof of that, really, it's coming from an equilateral triangle where you've got 60 degrees at all corners. And what do you know about equilateral triangles? This side's equal to this side is equal to this side. So if I split that, right, that's why I'm getting a 30, 60, 90. So this is, again, half the distance. If I called this a, this would have to be 2a. How do I find the height? I use Pythagorean theorem. 2a squared is 4a squared, minus a squared is 3a squared, and the square root of 3a squared is going to be a rad 3. So to finish off, what's x? Well, in this case, x is half my hypotenuse. So if I have 2a is equal to 600, then A would be 300, so that's my x, 300 miles. And then Y would be just 300 times square root of 3, which is about 519.6 miles.